so that we have a guide and we can pull some points from our two-dimensional graph. So what's changed, obviously, between what we looked at yesterday with the limicons and this one? 2 theta. Period has changed. So our period, which is 2 pi over b, is now pi. So we have a sine curve with an amplitude of 4 that has to complete one cycle by the time we reach pi. Amplitude of 4. Yet we're still going to be graphing our polar graph from 0 to 2 pi. So we need to plot both cycles. Now we have a frequency of 2, or 2 cycles completed by the time we get to 2 pi. So in labeling the points, we have 0, 0. We have pi over 4, 4. Pi over 2, 0. 3 pi over 4, negative 4. Pi 0. 5 pi over 4. 4. 3 pi over 2, 0. 7 pi over 4, negative 4. And 2 pi, 0. So we have a lot of zeros here, which is going to present itself in our polar graph as a lot of visits to the pole, to the origin. Yep. So, and actually starting at the origin, obviously, 0, 0. Then we have pi over 4, 4 as our next point. I cannot scale my circles. So when I loop from point 1 to point 2, I'm quadrant 1 with positive r's. So I'm going to loop through quadrant 1. Again, my two-dimensional graph never exceeds an amplitude of 4 or an r value of 4. So when I'm about to graph this, my graph is never going to go outside of this 4th circle with radius of 4. So almost like as I'm reaching that point, I like flatten out because I'm about to go on the decline. My radius is now declining back to the origin. So pi over 2 is here, paired with a radius of 0. So I need to get back to the origin right as my graph would have been about to touch terminal ray pi over 2. And then I jump into the second quadrant with a terminal ray of 3 pi over 4, but paired with a negative 4, which is going to pop us into the 4th quadrant. And that entire first portion, actually our entire second quadrant, has negative r values. So the entire second quadrant is going to be popped into the 4th. Again, I'm not going to go outside that circle with radius 4 because, again, even on the negative side, I don't have a larger radius than 4 or negative 4. So that's that point, and then I'm going to come back to the origin. And that's pi 0. And then I'm heading off to 5 pi over 4, 4, which is a 3rd quadrant angle with a positive r, so it's actually going to fall in the 3rd quadrant. And this is going to loop around through the third quadrant and then back to the pole. Still in the third quadrant with positive R's. Then 7 pi over 4 is a fourth quadrant angle, but paired with a negative radius is going to bring this back into the second quadrant. Oh geez, where did I just leave off? The third quadrant here. So then I continue up there, and then back to the pole. The name is fitting, yes? I don't know what you mean. Well, how about you, whatever hypothesis you got going on, why don't you test it in the follow-up examples, and if it holds true, I think that it's fair to make an assumption that it can work. The format for, I'm trying to think what variables they use, for all rose curves, sheet just written down, but I'm going to have to steal it out of the book. There's always an amplitude. I think they probably call that A. And there's always a change in the B value. The B value is not 1. Where's my row? R equals, we'll put this at the top, R equals A times the sine of n theta. Oops, there you go. Slash R equals A times the cosine of n theta. So anything that's of that format will be a rose curve. Limousin's had its own kind of format yesterday as well. Okay? I think maybe at this point it's already fair to say that your A value kind of gives you the length of each petal. Can we call these petals? Rose curve, flower, petals, makes sense. So I guess the length of your petals is your A value, pretty much. Because if this had a smaller amplitude, that would just make your petals go out less. Or if they were larger, it had a larger amplitude, your petals would just go out more. Okay? N is going to be a little bit trickier, which we will see as we look at more examples. So we'll talk more about that. Okay, here we have 4 sine of 3 theta. So our period here is 2 pi over 3. Which means a sine cycle has to complete itself by 2 pi over 3. Here's 3 pi over 3. 6. So this is 6 pi over 6, since I'm just counting kind of where our little hash marks are. We have 6. So 1 pi over 6, 2 pi over 6, aka pi over 3, 3 pi over 6, aka pi over 2, which is already labeled, 4 pi over 6, which is 2 pi over 3, and 5 pi over 6. So given that our period is 2 pi over 3, one cycle of sine needs to be completed by here with an amplitude of 4. So if I'm counting by pi's over 3, every other hash mark is 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, and 6 pi over 3. And then the only ones I don't have labeled are 7 pi over 6, 8, 9, 10, and 11 pi over 6. A little bit tricky there with the scaling and figuring out what each hash mark stands for, which we find out is pi over 6, and then kind of 2 pi over 6 changes, 3 pi over 6 changes because they reduce. So our second cycle has to finish by 4 pi over 3. And our third has to finish by 6 pi over 3. Lots of zeros again. So I'm not going to label all these points here. I'm starting at 0, 0. I have my graph pretty well scaled already. So this is pi over 6 paired with a 4. I'll loop through there. Now I have to return to the origin by the time I reach pi over 3. So when I'm about to do this loop, I cannot cross over pi over 3. I'm returning to the origin by then. So make sure your pedal gets back to the origin and never crosses pi over 3. So there is such a thing as making your pedal too fat. Okay? You don't want to cross pi over 3 because we've returned to 0 by that point. And then we go to pi over 2 with a negative 4. Which is that stretch. And then back to the pole by the time we reach 2 pi over 3. And we're dealing with angles leading up to 2 pi over 3, which are in the second quadrant, but they all have negative r's, which is why we're going through the fourth. We can't cross over 2 pi over 3's opposite ray, therefore. We cannot cross over 5 pi over 3. So make sure you keep this pedal skinny enough that we get back to the origin by 5 pi over 3, never crossing that. And then we head off to, leaving off here, we head off to 5 pi over 6 with a 4. And then back to 0 by the time we reach pi. So we're here so far. 7 pi over 6 with a negative 4. We already have that point, right? So this stretch here is just going to retrace over that stretch. And then we're going to get back to 0 by 4 pi over 3. Now technically, 4 pi over 3 is down here, but these are all negative r's leading up to it, which is why we're retracing over that section. And then to 3 pi over 2 with a positive 4. That's the same polar point as pi over 2 was with a negative 4. So we retrace that. And then back to the pole, we retrace that. And then when we're into our fourth quadrant with negative r, so we're retracing into our second quadrant. And then back to the beginning. Okay? So looking at those two examples, any hypotheses about what n means for us? Stephen? Like this one was even. So there are 4 petals. Okay, well, it does look that way. And then on this one, when it's odd, if it's an odd n, it's just that's the exact number of petals. Okay, we'll test that moving forward. How's your other shortcut going? Oh, so then we'll ditch it. It's not, I don't even know what it was, but, right. But you knew what it was, and now you know it's not really working out. Okay. Right, okay. All right, so let's flip to the back. Cosine. See if that changes our hypothesis at all. So, again, we have a period of 2 pi over 3. We're dealing with the same rectangular graph, so it's just going to be pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6 is what it is, 8 pi over 6 reduces, 9 pi over 6 reduces, 10 pi over 6 reduces, 11 pi over 6, and 12 pi over 6. So we need to get a cosine graph with an amplitude of 2 in by the time we reach 2 pi over 3. So cosine graphs start at a maximum, end at a maximum, have a minimum halfway in between those maximums, and zeros in between those extremas. So there's just one cycle. So we got to have another cycle repeating and completing by 4 pi over 3. And then another one by 6 pi over 3, aka 2 pi. Good. All right. Starting with a theta of 0 with a radius of 2. Can we scale this one? I'm going to scale it. 1, 2. And then we go back to the origin by the time we reach pi over 6, yes? So your petal approaches the pi over 6 ray, but never actually crosses it. And then we're headed towards pi over 3 with a negative 2. And then back to the origin by the time we reach pi over 2. And then off towards 2 pi over 3 with a 2. Oops. And back to the origin by the time we would have gotten to 5 pi over 6. Make sure you don't cross 5 pi over 6. Down to pi negative 2, which actually puts us back at the beginning. And then back to the origin by the time we reach 7 pi over 6. aka pi over 6, because that's its opposite ray. And so this seems to just be tracing over itself again. Yes? So let's go back to Stephen's hypothesis. Is it proving to be true with cosines as well? He said if it was odd, which 3 is, then that's the number of petals you should have, 3 petals. Do we believe him? We don't have any reason to refute his claim. We haven't done anything with 5, and we're not going to. So maybe we should just use our calculator to explore a little bit. It'll just help us do... I mean, we could do something with 5. Your scaling would be a little bit uglier, right? Because your period would be 2 pi over 5. But we could. It's not on the note sheet, so I'll just experiment this way. 2 cosine of 5 theta. Window. Do you see 5 petals? Yep. I wonder why that one looks kind of funny. Maybe just because there's a line through the middle of it, so it looks thicker, because the axis is going through it. Okay. Anything else you want to test?
8 petals.
8 petals would require an n of what?
According to Stephen's 16.
4. According to Stephen's
4.
philosophy. 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. I think Stephen's got it. Okay? What's that? I got a question for you. What's the difference between this 2 cosine 4 theta and 2 sine 4 theta? Get a good look at that. I'm not going to do them on the same graph at the same time because it would just be mass chaos. But I'm going to change this to a sine. Right. If the cosine one had its petals kind of coinciding with the axes, and this one is kind of straddling the axes, we don't have a petal right over it. So the cosine one, well, they're both symmetrical, so that's a bad way of... Wait, I like Adam seems like he's confidently trying to say something.
For the sine, you started at the origin, so that's, petals start at the origin with the cosine 1 line.
Ah.
At the maximum.
Right. So on the cosine curve, we start at a maximum. We start at a theta of 0, but a radius that's out here somewhere. So we start with a point on the x-axis, and therefore our petals coincide and kind of lie on top of our axes. Good stuff. I don't know that knowing that shortcut is, I honestly, knowing either shortcut is really only for the benefit of double checking yourself. It should all happen naturally with our two-dimensional graph. So last one, we expect, let's just cheat with this one. We expect that this one should have how many petals? 3 cosine of 4 theta. And do we expect the petals to be on the x-axis? Great. Good stuff. Okay. The only thing I'm trying to think if the period equaling 2 pi over 4, it's not really going to cause any sort of a hiccup with our scaling. You just have to get a full cosine cycle in here, another one in here, another one in here. So there are going to be 4 cycles, frequency of 4, which is the reason for the 8 petals. Okay? See, what happens when n is odd is the cycle sort of repeats itself, right? The first quadrant negatives, like let's say with this one, your first quadrant, that's a tough way of looking at that one because it's split. Let's look at this one. Your first quadrant positives get repeated with your third quadrant negatives. That's what happens when your n value is odd, which is why you don't have a double number of petals, because it overlaps itself, we saw. So your rose curve rules are as simple as if n is even, we have 2n petals. And if n is odd, we have n petals. And there was my cheat for the last one, which we don't have.